Symmetry and skewness in return distributions. Skewness or skew refers to the extent to which a distribution is not symmetric. Now, when you have a normal distribution, it has a skewness of 0, or we can say that a normal distribution is symmetric. What that means is we have an equal distribution on each side of the mean. This could be your mean, this is also the median, this is also the mode, and the distribution on each side is the same. This is symmetric, so the skewness is equal to 0. A positively skewed distribution is characterized by many outliers in the upper region or the right tail. This is called the right tail. Notice that we have several outliers over here. This is called a right skew. When you have a right skew or a positive skew, these outliers on the right pull the mean to the right. So the mean is going to be greater than the median, which is over here, which is going to be greater than the mode. Mode is the most frequently occurring item, so that is over here. This is the mode, and we essentially have this relationship where the mean is greater than the median, which is greater than the mode for a positively skewed distribution. For a negatively skewed distribution, we have a large number of outliers on the left. This is the left tail. What this does is pull the mean to the left. Therefore, in this situation, we have a mode which is greater than the median, which is greater than the mean. Let us look at a practice problem. Which of the following is most likely characterized by frequent small losses and a few extreme gains? We have just seen this. The correct answer is C, positively skewed, where we have a few large losses and many extreme gains, which represents the outliers on the right. Which of the following is most likely to be true for a negatively skewed distribution? And we just saw this. In a negative skew, you have a relationship like this, where the mean is pulled out to the left, the mode is over here, and the median is in the middle. So you will have a situation where the mean is less than the median, which is less than the mode. Now try this one. The correct answer is A. In the previous section, we've talked about skewness, which is a measure of symmetry. What we are looking at here is a normal distribution, and here this is perfectly symmetric. Therefore, we can say that the skewness is 0. Now, another very important measure is kurtosis. Kurtosis is a measure of the combined weight of tails relative to the rest of the distribution. We can have three types of kurtosis. A curve can be mesokurtic, leptokurtic, or platykurtic. The distribution we are looking at here is a normal distribution, and a normal distribution has a certain amount of weightage in the tails. If this weightage in the tails is the same as a normal distribution, then we say that the curve is mesokurtic. So let's say we have this distribution here, which is shown in red. Notice that this distribution has fatter tails, so there is more in the tails over here compared to the normal distribution. Such a distribution where we have more weightage in the tails is called leptokurtic. Also notice that a leptokurtic distribution is more peaked than normal. So that means that the probability of being a little bit on either side of the mean is more for a leptokurtic distribution relative to a normal distribution. The third category is platykurtic. Platykurtic distributions have thinner tails relative to a normal distribution. So the key points to remember: Mesokurtic means that the tails have the same amount of weightage as a normal distribution. Leptokurtic means that the tails are fatter than normal, and platykurtic means that the tails are thinner than normal. You also need to understand this term excess kurtosis. So as I said, this is a measure, so we need numbers. A mesokurtic distribution has a kurtosis equal to 3. So we say that a normal distribution has a kurtosis equal to 3. A leptokurtic distribution will have a kurtosis which is more than 3. So the fatter the tails, the higher the kurtosis. And this leads to a measure called excess kurtosis. Excess kurtosis is equal to kurtosis minus 3. If we say that a leptokurtic distribution has a kurtosis equal to 4, then the excess kurtosis will be 4 minus 3, which is equal to 1. Therefore, on the exam, you need to be careful as to whether you are given the kurtosis or excess kurtosis. If you are given excess kurtosis is equal to 1, you need to recognize that the kurtosis is more than normal. Also, if the excess kurtosis is 1 or more, then that implies that the kurtosis is unusually high, which means that the weightage in the tails is unusually high. Now there is one final point I want to emphasize. For these two distributions that we are looking at here, the mean is the same, the standard deviation is the same, the skewness is the same. The only difference is the kurtosis. So if I were to ask you between these two distributions which is more risky, the answer would be the one with excess kurtosis is more risky, because the probability of being here in the negative region is more for the distribution that has excess kurtosis, in other words, the leptokurtic distribution. Here are the sorts of questions you might see on the exam. Which of the following is most likely to be a measure of when a distribution is more or less peaked compared to a normal distribution? So all you really need to do here is remember the term. The correct answer, as you have just seen, is C. A distribution identical to a normal distribution is, and here again you just have to remember the fact that a mesokurtic distribution has a kurtosis of 3, and this is your normal distribution. The final section in this very long reading now, using geometric and arithmetic means. A geometric mean is appropriate for making investment statements about past performance. Now let us look at a straightforward example. Say you had $100 2 years ago and you had a return of 100% in year 1 and minus 50% in year 2. What was your mean return? If you simply take the arithmetic mean, then you will have 100 and then minus 50. So that is 50 divided by 2, which is equal to 25%. So the arithmetic mean is 25%. But look at what's actually happening. When you have $100, in the first year you get 100% return. So you end up with $200 at the end of the first year. But then in the second year you lose 50%. Which means that you are back down to 100. So in reality, you have not made any money. You started with 100, you end up with 100. So your mean return really is 0%. Arithmetic mean, however, is telling you that the return is 25%. So clearly the arithmetic mean is not the right measure when you are looking at returns over a period of time. A better measure is the geometric mean. So let's look at how we would calculate the geometric mean. If you recall, with geometric mean, you do 1 plus the return in the first year. 100% return means you just do 1 plus 1. Remember, a 50% return would have meant that we do 1 plus 0.5. So 100% return means that we do 1 plus 1. And then you multiply by the return for the second year, 1 plus the return for the second year, which is actually minus 0.5. And then you raise to the power of 1 over 2. We have 2 multiplied by 0.5 raised to the power of half. So what you have is 2 times 0.5 is 1. 1 to the power of half is still 1. And then you minus the 1 to get a rate, and you end up with 0. So your geometric mean is 0, which means that on average you are getting a 0% return, and that is a much more accurate depiction of what is happening. An arithmetic mean is appropriate for making investment statements in a forward-looking context. If you have $100 now, and the two possible returns for the upcoming year are a 100% gain or a minus 50% loss, what is the expected value? Here it makes sense to look at the arithmetic mean of 100 and minus 50 and to say that our expected return is 100 plus minus 50 over 2, which is equal to 25%. So saying that our expected return is 25% is appropriate. However, in the first scenario where we have time series data, there the appropriate measure is the geometric mean. So that is it. We are done with this reading. Just a few major summary points. We talked about measures of central tendency, and here you need to understand the various kinds of means. We talked about arithmetic mean, we talked about geometric mean, harmonic mean, the weighted average, and so on. You need to understand all these different kinds of means and how to calculate them. Then we talked about measures of dispersion. The most important measure is standard deviation. This tells us how spread out our data is. You need to know how to use the formula, but it is more important that you understand how to use the calculator to determine standard deviation. Recognize also that standard deviation is different for a population versus a sample. You also need to understand Chebyshev's inequality, which is 1 minus 1 over k squared. The k stands for the number of standard deviations, and the strength of Chebyshev's inequality is that it allows us to say how much data will be within a certain range, assuming without making any assumptions about the nature of the underlying data. And finally, you need to understand the basics of skewness and kurtosis. In terms of the work that you now need to do, go over the learning objectives outlined in the curriculum, go over the examples and practice problems, especially the shorter problems or the multiple choice oriented problems in the curriculum. The other questions might look a little bit difficult, and that's okay. At least read the solutions and try to figure out what the curriculum is trying to say. I would say it is more important that you do practice questions from other sources like Schwezer and try to do as many questions as possible to make sure that you are on top of this material. That is it.